Welcome to this obviously last seminar of the European Astrobiology Institute this year. And today's speaker is Brandi from the Jet Propulsion Laboratory in Pasadena in the US. Brandi did her PhD at the Tufts University in Boston at the United States, and then she moved in 2015 as a postdoc to Jet Propulsion Laboratory, where she still is now. She has been at this institution quite a long time, almost 8 years. And now she is working there as lead sample integrity scientist of the Mars Sample Return Program, as well as science systems engineer and scientists there at JPL. We also met at the inaugural meeting of the European Astrobiology. Well, that's me, and hope you will get lots of new information about this mission also out of that. The floor is yours, Brandi. Many thanks for coming at this early time in California.
Oh, thank you so much. Thanks for inviting me, Wolf. And I just mentioned that I met Wolf 6 or 7 years ago while I was still doing my postdoc at a astrobiology summer school in Iceland. So I'm very excited to be here and talk to you guys today. So, oops, sorry about that. So I'm going to talk to you guys a little bit today about the NASA ESA Mars Sample Return campaign in general, and then a little bit more specifically in the astrobiologically related planning that's going into getting ready to hopefully receive these samples from Mars. Hold on. There we go. All right. So again, I'm going to start with just a little bit of background. Many of you probably already know this, but sometimes I still get asked this question, why are we doing Mars sample return? Why can't we find out everything we want to know about Mars just with all the amazing missions that we've already sent there and with the meteorites that we already have on Earth? And of course, we've learned so much about Mars. I'd say we know more about Mars than any other planet besides Earth. But every time we send a mission to Mars, we learn something new, but it always leads to more questions and more detailed questions that we can refine. So there's a large set of scientific objectives that we think can only be achieved with samples in a laboratory. And we expect the results of these, getting these samples back on Earth, to be really profound. Now, in the area of astrobiology, the search for extraterrestrial life has always been a key driver of why we keep going back to Mars. But we know so much more now in terms of the past habitability of Mars, the potential for biosignature preservation, and more about extremophiles on Earth that make Mars even more interesting. And once we get the samples back on Earth, we can use much more effective search strategies than we can with rovers or orbiters. There's a lot of advantages. Anyone who's worked in a lab will be very familiar with all of these, but there's many advantages to working in a terrestrial lab that we don't have on spacecraft. Some of these things include sophisticated sample prep. We can get much lower detection limits, greater precision and accuracy, and also the ability to be discovery responsive. If you find something doing one certain scientific investigation, you can tailor your follow-up investigations based on the samples that you're looking at. And then, of course, there's a wide variety of instruments that just really can't be miniaturized to fit onto a spacecraft or to work well on Mars. And then, of course, the greater spatial resolution and focus we can get using Earth-based instruments like SEMs and things like that. So, again, one of the other things to keep in mind when talking about looking for life on Mars is, extraordinary claims require extraordinary evidence. You might find one thing that you think is an indication of life on Mars, but unless you find multiple pieces of evidence, it will be very hard for that to be convincingly sold as the discovery of life. So by doing coordinated analyses and looking for multiple types of biosignatures and multiple classes of biosignatures, we can get a much better idea of their significance. Of course, the most obvious is always, organic and biological molecules. But there are also, minerals that may be biotic. If you have extant life, you might have biochemical activity. Of course, we know some of the earliest evidence we have of life on Earth is in the stromatolites and such in Australia, which we find looking at textures and structures in concert with organics and mineralogy. Unusual chemistry, unusual isotopic patterns. Getting samples back in the labs on Earth allow us to look for all of these things simultaneously in a single sample, which is just something we can't do on Mars, at least with our current technology. So in response to this, NASA and ESA are working together very, very closely and very well, I might add, on a Mars sample return campaign, which is actually broken into several pieces and different projects. I think everyone is very familiar with Mars 2020, which is currently on Mars collecting amazing samples. We have a great return sample science team on Mars 2020 that's helping select the most scientifically interesting samples for return to Earth. One of the things I like about this slide is that it's really focused on the samples. I have a similar slide next, but again, we have, establishing the geology of the field site, but we have sample selection, the documentation of the sample context with the in situ data. So when we get the samples back, we'll have a great amount of in situ data about each, and then delivering the samples or placing them in depots on the ground. You may all have heard the news that Mars 2020 is actually currently in the process of beginning to place the first collection of samples at an area of Jezero Crater known as Three Forks. This will kind of be a small set of about 10 samples that will essentially serve as a backup for sample retrieval in case something happens to Mars 2020 down the line. But the general plan is for Mars 2020 to keep on collecting samples to eventually traverse out of Jezero Crater toward Midway and collect about 30 samples on board. That leads to the next segment of Mars sample return, which is known as the Mars Sample Return Program. Again, this part is a joint NASA-ESA partnership. There's two missions involved here. One is the sample retrieval lander, and again, I apologize for the old picture here. You see there's still a sample fetch rover here that will now be replaced with a sample retrieval helicopter or two. But this lander will land on Mars. In the nominal case, Mars 2020 will drive to the sample retrieval lander and basically pass the samples directly from the Mars 2020 sample collection to a European sample transfer arm, and it will be put into a Mars ascent vehicle, so basically a rocket that will launch the samples into orbit. And then the Earth Return Orbiter contains a subsystem known as the Capture and Containment System that will basically catch the orbiting sample container in orbit, put it inside ERO, and then basically fly back to Earth and then release an Earth entry vehicle containing the sample container that will land on Earth nominally in 2033. Now, science has obviously had a big part in these three segments of the mission, but one of the hardest parts to plan from the science perspective and the most complicated parts is this sample receiving project over here on the right. So this is basically encompasses everything that happens after the samples arrive on Earth. So a sample receiving facility, which would be a biosafety facility that would be used to carry out a sample safety assessment to make sure there's no biohazards, preliminary examination of the samples, and then sample curation and some competed science inside and outside of this sample receiving facility. I'll get into more detail into that later, but this is just the general overview of the Mars sample return campaign. I will point out that the sample receiving project is in its early phases right now. This is also a joint NASA-ESA project. The partnership is becoming more clear now that the ESA ministerial has happened, and this has kind of been endorsed to continue on, and we're working very closely with our ESA colleagues to make sure that this is an equal partnership. So again, this is just kind of the same kind of thing, the field analysis, documentation. It's a little bit of a complicated campaign because there are actually transitions in sample custody, as we call it, where different programs or projects are responsible for the samples. But we're all working very closely together to make sure that this is a cohesive campaign as well. Okay. So in terms of MSR science, the planning for this has been going on for decades, but more recently there's been several committees, joint NASA-ESA partnership committees that have defined a set of guiding principles for MSR science to make sure that although this is an amazing engineering mission, that the science is maximized and that we get the best science out of the samples, and that the scientific benefits are shared around the world and not just in the US, not necessarily just in the US or Europe either. So the main guiding principles that we use to drive everything are, transparency. We want everyone to know what's going on all the time. How to participate is clear. Of course, maximizing science. We want to maximize the limited amount of sample mass we'll get back. We're talking about, several pounds of samples. It's not like Apollo where you have, hundreds and hundreds of pounds of moon rocks. There's going to be a limited sample mass, and we want to really optimize the productivity there. Accessibility is a big one, especially considering the samples can only land in one place initially. There'll likely be one initial biosafety facility where all the samples will go at first, but we want to make sure that there's accessibility, that international scientists can be present and can be, an integral part of the team, and that we have a variety of opportunities for international scientists to compete or through other publicly accessible activities. Another key point here is that although the samples, may eventually be split and be stored in multiple places, one of the important things here is that Mars 2020 is optimizing their sample selection to bring back a collection of diverse samples. Not every sample will be good for every purpose. Of course, there are igneous samples, sedimentary samples, regolith samples. These samples are kind of collected into suites where you can learn as much about Mars from the differences between samples as the similarities. So it's important that the samples and associated witness blanks and contamination knowledge be managed as one collection, even if it's physically in other places. And then, of course, for our management partners, we need to remember to have some kind of return on investment, right? We need to have demonstrable benefits. This is not an inexpensive or easy thing to do, and so our government overseers very much care about having a return on investment, whether that be through industry tie-ins or scientific return and acclaim for their country scientists and things like that. So these are things we keep in mind at all times when we're planning for the science of Mars sample return. So to get to more into the astrobiological considerations here, there are actually a lot of them, and they started many years ago when Mars 2020 was first designed. So there are, many important considerations here. These are not necessarily all of them. These are some that have been, worked on recently. But of course, one important thing in making sure we can do the scientific investigations we want to do is particularly in the area of organics for astrobiology and biosignatures is limiting our organic and biomolecule contamination and having good contamination knowledge so that we know what the terrestrial contamination of the samples is likely to be. And this applies to all the missions. So I'll talk a little bit more about that. The same thing with avoiding environmental extremes that could alter or degrade biosignatures, things like high temperatures that might alter the samples to the point where we can't get good results. So we also need to think about the measurements and investigations needed to complete the sample safety assessment. So an important consideration for Mars sample return, because Mars may host extant life, is that we need to handle these samples, at least initially, as if there may be a hazardous material in the samples, biologically hazardous material in the samples. So it's really important that we have a well-defined sample safety assessment procedure to determine if that's true. In which case, a lot of measurements will need to be done inside biocontainment if the samples can't be safely released, or the samples, alternately, some subset of the samples can be sterilized and sent out for things. So in order to know what is feasible in that area, there's been a lot of work to determine which, if any, measurements could be performed on sterilized samples outside of biocontainment. I give you a spoiler that I don't think is really going to be a surprise. Most biosignature related measurements would be altered by most, well-known sterilization procedures. So a lot of those things need to be planned to be done inside biocontainment in one way or another. And then, of course, we've also discovered that there are some measurements that are time sensitive, and we need to plan for a sample workflow that allows us to make those measurements before information is lost. Okay, So I'm not going to go into a huge amount of detail on contamination control and knowledge. This is mainly just to acknowledge that it's important and it's been considered. Mars 2020 had extremely stringent requirements on contamination that could be on the sample tubes and other things that touch the samples themselves. The program flight missions, so the sample retrieval lander, the Earth return orbiter, the capture and containment system, also have strict contamination control and contamination knowledge requirements to minimize contamination that could get into a sample tube, and also to characterize any potential contamination. This includes witness blanks that have been carried by Mars 2020, as well as a witness plate that will be in the orbiting sample container that will, for lack of a better word, witness the round trip contamination in the flight canister. Again, one of the places this is going to be most complicated is within the sample receiving facility and the sample receiving project as a whole. To clarify terms, the sample receiving project encompasses everything that happens once the samples land on Earth, from transport and investigations that happen all around the world. But the main piece of it, the biggest piece, is the sample receiving facility, which is the biocontainment facility. The contamination control and knowledge problem becomes a little bit more difficult in the sample receiving facility than it does on spacecraft, because of course you have humans and terrestrial biology present in here. So the strict CC and CK requirements for the sample receiving project are currently in development. We've actually just kicked up a committee to start working this problem in more detail and to work closely with the SRF building engineers on how to implement the best contamination control and knowledge that we can for the samples. This is going to be particularly important for things like the sample safety assessment. Terrestrial contamination is likely to cause false positives in the samples, and so we need to be really careful of that, so we don't assume that the samples are hazardous or that they contain extant Martian life if they don't. So this is a really important consideration. Sample environmental control, again, this is something that has had implications for Mars 2020, as well as for the flight missions, and then for the sample receiving project. Perhaps most importantly for biosignatures is thermal degradation or alteration of organics when you get to temperatures that are significantly higher than the samples have seen in their natural history. So the MSR program has a max temperature requirement of 30 degrees Celsius during the retrieval and transport of the samples to Earth to minimize thermal alteration. Another important one is impact and vibration. So these are called dynamic environments from an engineering point of view, but the key here is that it's important to preserve the samples intact as much as possible so that we can look at the stratigraphy, the textural information, the spatial relationships between pieces of the samples. And so all parts of the campaign have requirements to limit the amount of fracturing and vibrational powdering of the samples so that we can get the highest quality samples and the highest quality science possible. Excuse me. So actually, I'm going to skip that one for now. Well, actually, no, I'll start here. So most of what you're going to see in the rest of this presentation is work that was done by a committee called the MSR Science Planning Group Phase 2, although I'll also cover some of the COSPAR Sample Safety Assessment Protocol Working Group report. A lot of what the focus here is what needs to happen inside the sample receiving facility. And this is kind of a high level summary here. You know, we get the return spacecraft. Everything inside this red line is a biocontainment facility. And these are all the things that need to happen in here with high contamination control, including, you know, taking apart the spacecraft, getting all the dust off of the tube so that we can do science on that, preliminary examination, the sample safety assessment. I'll go into more of all of this, but the general idea here is to produce a sample catalog and to eventually get all of the samples outside of containment once they're hopefully deemed safe, where we do hope that most of the science happens outside containment. So the goal here was to look at what's the minimal set of things we need to do in the SRF to make sure we don't lose our opportunities to do any of the key science. So all of this work has been published in a special issue of Astrobiology, which, oh, look at that. I actually have a copy of right here, and I can put the link to this in the chat later. So this is a substantial document that includes, I think, 9 papers on various aspects of this. So if you want more information about any of these pieces, it's all open access and easily available. But the first piece that I'm going to talk about here is the initial sample characterization. So again, this is things like measuring the, weighing the tubes, potentially taking CT scans of the samples while they're in the tube to get some chemical and mineralogical information, as well as spatial information, opening the tubes, capturing the headspace gas in the sample tube so that we can do analysis on the gas phase as well, weighing the samples, measuring the samples, and doing some initial measurements of the samples. So this is really key for a lot of reasons. And one of the main reasons is that because we have such limited sample mass, it's really, really important that we pick the right pieces of sample to do each analysis on. For example, you don't just want to take a random piece of rock and put it through a whole bunch of organic extraction procedures, only to find out that the rock had no or very low organic component in it in the first place. So this is really key to get your context so that when proposals are made to apply to receive certain pieces of the samples, the right pieces of samples can be allocated. And this is a really, really important thing that just we have to do. Okay, so I'm going to talk a little bit about the sample safety assessment framework. I'm not going to go into a huge amount of detail on this because I actually wasn't a member of this committee, but if you have any questions about it, I'm happy to refer you to the authors here. But the main key here is the objective here is to evaluate whether any of the samples returned from Mars could be harmful for Earth systems. So for the environment, the biosphere, organisms, geochemical cycles. And the main difference here between the scientific search for life and the sample safety assessment is that when we as scientists do investigations related to astrobiology, we start from the null hypothesis that there isn't any life in the samples, and we have to prove that there is. From a safety standpoint, the assumption is that we assume that there is harmful biology, extant life in the samples, and we have to disprove it. So that's the primary difference between the planetary protection approach to looking for extant life and the scientific approach. So there's 4 main principles as outlined in this report. It's to use a hypothesis-driven approach in the development of life detection. And again, as I just mentioned, to start from a positive hypothesis. We assume that there is Martian life in the samples, which is complementary to the scientific null hypothesis. One of the really key things here, though, from a scientist's point of view, at least from my point of view, is that all the measurements we need to do the sample safety assessment are scientific measurements. So there's a huge overlap between, just general astrobiological science investigations and the sample safety assessment. So the way we actually envision this happening is that the science, the actual measurements would be done by science teams who propose to do measurements of the samples. And then that data would be used by regulatory government agencies to determine whether it can be proven that the samples are safe. And so again, this is a very data-driven process, and but we envision that all these measurements would be done by competed science teams. So again, there's a whole integrated test sequence here. If you look, steps 1 through 3 are basically 3D structure, analysis of headspace gas, and basic chemistry and mineralogy. So these 3 steps, there's a high degree of overlap with what I called the initial sample characterization in the previous things and the previous slides. These are the things we need to do to determine which samples to proceed with for the next set of investigations. So the steps 4 through 6 are very focused on organic molecules and kind of looking for biosignatures as we understand them here on Earth. And then steps 7 and 8 are basically focused on life detection techniques. So again, life as we know it, which uses all of this information gained in these steps, and then agnostic life detection techniques as well, because of course, if there is extant life on Mars, we can't be positive that it looks very much like life on Earth. So this is kind of the test sequence as envisioned by the COSPAR Sample Safety Assessment Framework Working Group. And you can see there's a pause here at the end, where this is where we evaluate all of the data that's been collected and see if we can determine if the samples are safe. So I'll get to this at the end. Okay, so the other kind of thing we looked at was what scientific investigations that we know we want to do as part of MSR are sterilization sensitive. In other words, what measurements would we want to make where the thing we're measuring would be altered by sterilization, whether that's heat sterilization, so high heat sterilization, or gamma ray sterilization. Our hope is that we do the minimum number of measurements inside the sample receiving facility, the things that are needed for the sample safety assessment, and we determine that there are no biohazards in the samples, in which case, you know, we can do every other measurement outside of biocontainment in labs around the world where we have the best, most customized instruments and the best scientific expertise. But there is a non-zero chance that some things that the samples will not be deemed safe, whether because there's life in the samples or because, you know, we just can't conclusively rule it out. So the nominal situation or the thinking here is that any measurements that are found to not be altered by sterilization, we can take small pieces of sample and sterilize them and send them out. But anything that would be altered by sterilization, we have to think about whether we need to do those things in the sample receiving facility or not. And the reason we have to do all this planning in advance is that building a sample receiving facility is a very long lead time activity. The design process, or some of the design process, is already starting now. I mean, this is likely to take, you know, right up until the samples get back to get this building up and ready to go. So we need to know these things now, even though we're not expecting to see the samples for another 11 years or so. So I just said most of this, but again, if we don't plan to measure these sterilization sensitive attributes inside the SRF, we could lose important information. So this subset, or this sub-team of the MSR Science Planning Group 2 was focused on identifying the sample attributes that are vulnerable to alteration if you use heat or gamma. And then we also identified the overlap between things that are time sensitive and things that are sterilization sensitive. And I'll talk more about time sensitive things in a minute. But there were four main categories of kind of things we want to measure that we'd be worried about altering if we sterilize the samples. And of course, the main ones here are biosignatures of extant or extinct Martian life. I mean, extant life, obviously, if you sterilize it, you've significantly changed the signs of extant life. But extinct life also. Also, things like sample tube, headspace gas composition, other indicators of ancient or paleohabitability and biosignature preservation potential, and things that are volatile, rich, or amorphous material are also subject to change, especially when you're talking about high heat. So the main finding of this group was that most aspects of MSR science could and should be performed on samples that have been deemed safe, either by test or by sterilization, in uncontained laboratories. But some aspects of MSR sample science would be time sensitive and sterilization sensitive. And the main subset of these things that are sterilization sensitive are the things that we as astrobiologists care the most about. Signs of life, habitability potential, volatile exchange process, and things like that. So again, the approach here is that the four categories of measurements that were identified as being vulnerable to alteration, what is our approach to planning for those? So certain biosignatures of extinct and extant life. All the measurements here that are identified basically have overlap with the measurements that are needed for the sample safety assessment, and they're also time sensitive. And in other words, they're things that can change over time once you open the sample tubes. So all of these measurements need to be planned for inside the SRF. Same thing with the headspace gas composition. Now, the composition here, in terms of being time sensitive, it's mostly due to the fact that there is no such thing as a leak-proof vessel. And so, you know, the headspace gas composition will change over time to some extent. Some of the measurements related to paleo environment, habitability, biosignature, preservation potential are time sensitive and sterilization sensitive, whereas some are not. So we plan for some of these things to happen inside the sample receiving facility. So here's the main strategy that's been proposed here, is we need the SRF absolutely to contain the curation related things. In other words, the things needed for sample characterization, the things needed for sample safety assessment, things that are time sensitive so we don't lose that information, and the sterilization sensitive science that overlaps with the above. Okay, so this is the initial concept for the SRF. Once we run through the sample safety assessment, we say, okay, can we now release the unsterilized samples? If the answer is yes, great. Then all the sterilization science, sterilization sensitive science that wasn't done in these initial steps can now be done in uncontained laboratories anywhere in the world. If it's determined that we can't release unsterilized samples, we can sterilize and release some samples to do the sterilization tolerant science that we didn't do inside the SRF. And then we need to figure out a way to add some contingency capability to do other sterilization sensitive science. Now, one of the great things here is that, you know, if we find signs of extant life in the Martian samples, you can imagine many of the budgetary constraints will go away. So because we are driven by budget and cost and schedule here in terms of we only want to build an SRF that's as big and as complicated as we need it to be for many reasons, and not least of which is the fact that most scientists would rather work in their own laboratories, and we're likely to get better science that way. But if it's determined that we can't release unsterilized samples, we need contingency capability. So we can potentially think about having biosafety containers that would allow you to transport the samples to other facilities. You can think about, you know, an additional modular building that could have more instruments in it, and things like that. So the initial goal is to basically plan for as much science as possible outside the SRF, but have backup plans in case that isn't possible for whatever reason. So okay, again, I'll talk just a little bit about time sensitive science because I mentioned it a little bit already, but we know that breaking the tube seal, once we extract that headspace gas from the tube, there'll be an equilibrium change that will cause, you know, things to outgas from the samples. The samples will be stored under some type of curation gas, which is likely to be very dry. So things like dehydration reactions are likely over time. Mineral volatile exchange here is one of the big ones, as well as, you know, degradation of organic material, although we'll limit that to the best of our ability. So again, this is a separate sub-team that worked on this, and they basically were asked to determine kind of the time scales of processes that would alter the sample and that would impede our ability to make measurements. And you can see there are several things here that have been identified as basically needing to be measured on the scale of hours, days, or weeks. And so we don't expect the samples to be released from the SRF within the first several weeks. So these are things we all need to plan for inside the SRF as well. Like we may have degradation of organic material. Of course, this depends a lot on the composition of the samples. What's the water content? What's the reactive oxygen content? The oxychlorines, things like that. Already mentioned leak rates. And again, the exchange of H2O from sulfates, perchlorates, and clay mineral interfaces, and then the host of those volatiles. So these are also things we want to measure as quickly as possible. So again, this results in kind of a footprint of kind of the things that you would have to do in the SRF. Of course, you need to receive the spacecraft and take it apart. You need to provide an environment that consists of BSL-4, so this is biosafety level 4 equivalent containment, and a very high level of cleanliness and contamination control. Now, this is not something that is typically done. Most biosafety level 4 facilities are not super worried about contamination of their samples. They're worried about things getting out, not things getting in. So the SRF is really kind of a first of its kind thing where we need to worry about obviously Mars sample material getting out and also terrestrial contamination getting into the samples. We need to make sure we can put all the samples into a safe and stable state and complete the initial characterization, and then do specific science investigations, those needed for the sample safety assessment. And then we need to be able to enable the sample allocation process and the pristine storage process so that we can start allocating those samples for analysis outside the SRF, as well as for long-term curation. And again, okay. So again, this is just a thing here. And of course, at the end, what we really want is these amazing scientific results that we know are going to come from looking at these samples. So subsequent to this MSPG2 committee, which wrapped up about a year and a half ago, 2 years ago, there was a whole bunch of next steps outlines, some of which have already had progress made on them and some of which are still in progress. One of the key recommendations was to finalize and start implementing an overarching MSR science program. So this included, official documents between NASA and ESA that define the MSR science program and the roles and responsibilities. The primary documents here were a science MOU, which was signed, and an MSR joint science management plan, which has also been completed and I believe is in the signature process. And of course, to seek the necessary funding and authority to implement them. So as we all know, the ESA ministerial meeting went very well. The NASA budgeting process, of course, happens on a different schedule and happens yearly, but we do have initial budget allocations for the ongoing planning for receipt of the samples. From a science standpoint, it was also recommended that an MSR campaign science group be formed. So I'll talk a little bit more of that on an upcoming slide, but we do have now an MSR campaign science group. The members were selected in spring of 22. We've had one in-person meeting so far. This group basically functions in an advisory capacity to the NASA and ESA MSR lead scientists. Like I said, I'll talk more about that in a minute. The sample receiving project, which will be responsible for everything that happens to the samples once they arrive on Earth, is in a pre-phase A state right now. So the organizational structure, the NASA-ESA relationships, and the funding are still kind of being finalized. This project is going to be led by the Johnson Space Center on behalf of ESA and NASA's Mars Exploration Program. The science office for this project will be run here at JPL. But again, all of the official org charts are being finalized. We're expecting to proceed officially to phase A around next June. So we'll have a mission concept review where the initial concept for the sample receiving project will be presented, and hopefully we will officially then proceed to phase A, where we'll get into more detailed design and planning for the specifics. Another big one that's kind of been lagging here because there's not a dedicated research program for it is funding research and development and research and analysis activities for MSR science. So, we're looking to utilize and or augment existing funding mechanisms, and ESA has allocated some funding for this, as has NASA, but we're looking to ramp this up. There's technological developments, of course, but there's also analog studies that need to be done. We need to really optimize the workflow and processes so that so when the samples get back, we're ready to use them in the most efficient way possible. We don't want to waste samples practicing on them. So we really need a well-funded RNA and R&D program for this. And we're working on a roadmap for that right now with the Joint Science Office, which we have a joint NASA-ESA Science Office that works in conjunction with the MSR Campaign Science Group, and we're currently working to kind of finalize that long-term R&D RNA roadmap, and we're hoping to tell you more about that in the next several months. And then, of course, we need to continue to advance the science-related requirements for the SRF and for SRP, especially regarding the things I've mentioned earlier, the environmental conditions that are allowable, what kind of gas will the samples be stored under, how much contamination can be allowed to get into the samples and into the instruments. And then we need to translate this into a really comprehensive curation plan, facility concept budget, and put that all into schedule planning. And so that's an ongoing thing, and that will continue to be ongoing for the next several years. So again, I talked a little bit about the Joint Science Management Plan. So this actually covers the implementation of MSR science and sample management, including the interface to Mars 2020, et cetera. So again, this includes agreements between NASA and ESA on the overall science and sample management structure. And again, one of our key goals here, maximizing the participation and the number of opportunities for the science community to participate in the planning. So again, we have things like this MSR Campaign Science Group that I'll talk about more in a minute, that will be recompeted every few years. So there'll be ongoing opportunities to get into that. And then I believe starting as early as I want to say 2026, we're thinking AOs, announcements of opportunities to propose instruments and measurements to be included in the SRF. And so we continue to think about how to maximize those opportunities for the science community. And then, of course, there's data, publication, and communication policies. And this is really, this joint science management plan is really based heavily on those 5 guiding principles I talked about earlier. And again, there's a reference here. There's a lot more detail about this in the astrobiology special issue I mentioned earlier as well. So again, the MSR Campaign Science Group, it's co-chaired by the NASA and ESA MSR lead scientists. Currently in those roles are Gerhard Kaminik for ESA and Michael Meyer for NASA. And this Campaign Science Group assists these scientists in the execution of the science management plan. The main objective here is to ensure that science is engaged at every point in the process so that we can really maximize the science potential of the samples. And so we have a good scientific rationale for all of the sample related decision making and all of the processes that happen across the whole campaign. So again, this MCSG functions in an advisory capacity, and it's also a scientific resource for the flight missions and for the ground-based products. The first major activity that MCSG completed was the Mars 2020 MSR Sample Depot Caching Workshop, which happened a couple months ago. And that's the one that resulted in the recommendation to deposit an initial set of samples at Three Forks, which I mentioned at the beginning of the talk. The main role of MCSG here was to kind of evaluate this proposed subset of samples that would be placed in this depot, and to evaluate and propose to the science community whether this represented a scientifically return-worthy collection. Should the worst happen and we're only able to get 10 samples, would MSR still be worth doing? The answer was a resounding yes, by the way, which was great news for everyone. So upcoming things that this MCSG will be working on include planning for the contamination control and knowledge requirements and the instruments in the SRF. So we expect in the coming months that there will be a committee that I mentioned is just getting underway for contamination control and knowledge. There'll be a part 2 of that committee later. And then we envision there will be something along the lines of a measurement or science definition team that will be advertised, will be chartered by MCSG, and will be open to competition and participation from the science community as well sometime next year. So be on the lookout for that. So again, this is our MCSG. I mentioned Michael and Gerhard. We also have this joint science office, which is a part of the sample receiving project, and this includes myself and the acting project scientist Dave Beatty, and his ESA counterpart, the ESA project scientist Elliot Septon-Nash, my co-deputy Fiona Thiessen, and then Tim Haltigen, who is a Canadian but operating here on behalf of ESA in his role. And then we have a set of selected members. We have, it's about equally split between US and European participants. We do have Japanese as well, Japanese participant as well. And then we have several ex officio members here, which is really important. We have CDC membership, we have Mars 2020 membership, we have Minnie Wadwa, who's the principal scientist for the flight missions. And then we have curation counterparts, Andy Harrington and Aurora Hutzler. So this is our kind of way of making sure that all of the eyes that are on the decisions are the right eyes and that we don't miss anything. So we have these ex officio members as well as our selected science community members. And again, I mentioned this already, but for the sample receiving project, it's going to be managed by Johnson Space Center in a coordination with NASA and ESA. We are, like I said, in a pre-project phase for this, but in this pre-project phase, we're doing some of the really important work here, like defining the project level objectives for SRP, as well as the specific scientific objectives and the requirements that are needed to meet the scientific objectives. And we're doing this, again, jointly between NASA and ESA, but also with science and curation, because these are, both very important stakeholders in this project. And I think that is probably my last slide. Yes. So if there are any questions, I'm happy to take those as well.
Yeah, I've actually not started with a question. I mean, I can remember in the early days of the mass sample return, there were lots of discussions about possible contamination of the Earth by Martian microbes or viruses. I mean, I don't really know the status of the discussion in the public at the moment, but is this still now a big issue, even given the current pandemic? I think people are probably even a little bit more worried than they were about those things.
Yeah, it's a really interesting question, because of course there are some people who have long been concerned about, you know, contamination of the Earth. I think from a science perspective, we you know, it's somewhat more clear to us that, you know, the Mars near surface is not super habitable, at least for life as we know it. But we do have to go through and assume that the samples may be hazardous. But from a public perspective, we do, at least on the U.S. side, we have to have these NEPA public meetings. So that's the National Environmental Protection Act. And there's been a series of public meetings that Mars Sample Return has had. And actually, surprisingly, the concern has been minimal. These meetings have not been heavily attended. They have not been controversial. There seems to be at least pretty wide acceptance that that NASA and ESA are doing this the right way and being as careful as possible. We have strategies for you know, 2 layers of containment between any Mars material and the Earth, and then of course we will continue to have to go through regulatory processes for these for the sample receiving facility to ensure that that's safe as well. But we haven't had a lot of you know, public uproar about this, at least not yet, which has kind of been a little bit surprising to me, frankly. But yeah, so far it seems that the public is trusting. So trusting NASA and ESA, which I think is really great. I think at some point there are always going to be people who don't trust anyone, but I think for the most part we're in pretty good shape on that.
So there is a question also via the chat by Nina Kopacz from Utrecht University. Thanks, Nina, for asking this, and I'm reading it out. I was curious, what are the geographical requirements for the SRF? Will it be at the Johnson Space Center, for example, or rather somewhere in the Canadian or Icelandic wilderness?
So there is actually no requirement yet. So there's, this is nothing that I'm even aware of. I know they are looking at several different potential places for this. It's not likely to be at Johnson Space Center. It is likely to probably be somewhere more remote. The only thing I think that we are assuming at this moment that the initial sample receiving facility, at least where the samples are first delivered, is likely to be in the United States, because the sample capsule is planned to land here in the United States. And so, you know, we would want to be close by and not want to mess with international shipping and things like that. So I do expect it to be in the United States, but we don't have a final answer on that.
Thanks a lot. So I think there's another question by Giuseppe Marante, which I can read out. What is the time scale for really recovering the samples, and does the needed technology already exist?
Yeah, that's a great question. So we have, as I mentioned earlier, 2 flight missions that are currently in development. So the sample retrieval lander is being led by NASA with an ESA provided sample transfer arm. This mission is currently in let's say phase C. So we're still in development. We recently, we're planning upcoming our PDR, which is our preliminary design review. So yeah, we do think all of the technology exists here. The plan is for that sample retrieval lander to launch from Earth in 2028. That's the current planning, and the Earth return orbiter is actually further ahead in its schedule, the ESA-led mission, and that one is meant to launch from Earth, I believe, in 2027. The plan is that these would rendezvous, you know, at Mars, and that the samples would be returned to Earth in 2033. So that's the notional timeline.
Yes, there is another question now. Mariana Battistuzzi, thank you for the presentation. is it your task also to develop a communication strategy towards the public and governments in case you find extinct life on your samples?
Yeah, I mean, I wouldn't say it's just my job, but I would say this is something that the MSR campaign and the project actually have already started working on in terms of communication strategy, at least at least now from the planetary protection aspect. It's kind of a very interesting thing, because one of the reasons we want to look at the samples from Mars is because we want to find signs of life, but we also need to of course, Mars 2020 is a surface or near surface mission, so we don't expect there to be extant life in the samples. But at the same time, from a science perspective, it would be amazing to find extant life to find Martian extant life in the samples. But from a potential biohazard standpoint, it's the other way. So it's an interesting communications challenge to talk about wanting to look for life on Mars, but also to say, we're pretty sure that the samples are safe. So there's a lot of political and communication aspects that go into this, and of course, as scientists, you all know that there's a difference between communicating with other scientists and communicating with funding agencies and communicating with regulatory agencies. So yeah, there will have to be a very comprehensive communication strategy. And then I think you have a good point here in terms of thinking about what would the communication strategy be if we actually think that we found signs of extinct or extant life? And also thinking about, how conclusive do the results have to be to make an announcement like that? Different people have different ideas in their mind of, what the threshold of proof, is. Some people think we've already found life on Mars. So it's a very interesting question. It's going to take a lot of advanced thought, and I think a lot of engagement with the science community too.
Yes, I think that's actually, to my mind, that's actually something that I'm more worried about, that people come out with preliminary statements which then are which then might be falsified afterwards, and this might be a huge damage for
Yeah,
the mission.
I agree, and that's something that we need to be prepared for, and especially from the science teams that are selected, we'll have to have very clear, a very clear communication and team guidelines and team rules. Oh, and sorry, before I end, Wolf, I just wanted to say that I will be at the Beacon conference and be able to talk more about this there, as will Gerhard Kaminik. So we encourage you guys to submit abstracts to that and to join us there.
Yes, please do, because I mean, it will be not only a very scientifically a very exciting meeting, but we will also be at a very nice venue, which is also astrobiologically very interesting, offering fresh volcanoes with lava fields, as well as extreme environments like salines and Mars-like landscapes, and also as telescopes. So we have something for every astrobiologist there. So it would be great to welcome you there in La Palma. And last but not least, we have also bursaries for early career scientists and students in the to actually attend the meeting. At least we can cover meals and accommodation, which is already quite much for early career scientists from EAI institutions which are presenting talks and posters. So please submit. With that,
I'm sorry, I see one more question from Nina. Actually, Nina, I'd love to talk to you more about this. So she just asked, can the samples be opened in a Mars chamber under Martian conditions instead of just under a neutral gas flush? Would that help mitigate the reactions in the sample, in the time-sensitive samples? And actually, that's a really interesting point. And I think that this is something that also is going to just require more thought and planning. It may be that different samples are open under different conditions. But again, somebody talk about that. And Nina, please write to me offline if you want to talk more about that or anything else.